second number here. And today we'll be talking about greatest common divisor, lowest common multiple, and some tricks you can do to find them, including the Euclidean algorithm. Okay, so basically I got this from my slide, but the greatest common divisor, or like some of you might know as greatest common factor, is the greatest positive integer that divides both of them, or like is a factor of both of them. And when we say a like that slash thingy b, we mean a divides b, or a is a factor of b, like you can see here. So 3 divides 6. So this notation will be quite useful today, and yeah. And we can define this as it means that b equals a times k for some integer k. So yeah, I'll have an example. So just answer yes or no. You can unmute yourself or type it in the chat, okay? Does 1 divide 2?
Yes.
Yeah, okay, good job. So 1 can divide any number, so 1 does divide 2. Now, does -1 divide 2?
Also, yes.
Yeah, okay, good job. So do you want to explain why?
Because -1 times -2 equals 2, and -2 is an integer.
Yes, good job. Okay. Yeah. I think you guys all understand this notation then. And yeah. There's also, once we find the greatest common divisor of stuff, we denote it as GCD of like A and B. I think that's like kind of self-explanatory. We'll get used to it when we like do some problems. And similarly for lowest common multiple, you also denote it like that. And when A and B are coprime, it's basically when GCD of A and B equals to 1. And yeah, the minimum of A and B is just denoted as min A comma B, and then the maximum is denoted as max A comma B. So for example, min of 1 comma 2 equals to 1. Yay. Okay. Wait, I should also be giving out cookies today. You guys like cookies, right? From Sophie's lecture. Okay. So here's some warm-up questions. I'll just give you guys 2 minutes to do it. Oops, sorry guys. Yeah, so you guys all got the first 2 questions right. Good job. Um, does anyone want to explain? Yeah, okay. Just feel free to unmute yourself.
So the first question, 12 and 18 are all divisible by 6, but 12 isn't divisible then by any other higher number except 12 itself, and 18 isn't divisible by 12, so it equals 6.
Yeah, good job. I'll give you some
Next one,
points.
same thing as this one, 24, because 60, never mind, that's 12. Because 60 divided by 12 is 5, and 144 divided by 12 is also 12, and you can't divide them by any higher number.
Yeah, good job. So
One
how
in.
did you do it? Did you list out the factors?
I just looked at what number is the highest that you can divide it by. Because 12, you can't divide 60 by any higher number that's also divisible by 144.
Right. Okay, good job.
This
So
one,
what you did
number
there,
is in, right?
it's one actually, but N is a good try. And but you brought up a really interesting point there. When you said, for example, for 60 and 144, you said 12 times 5 is 60 and 12 times 12 is 144, right? And you said it can't be divided any further, which is like a really interesting point because you get left with 5 and 12. And whoa, they're co-prime. Yeah. So that's very cool. Will the cookies increase exponentially? Perhaps. Depends how I feel. Maybe they will increase linearly. Okay. Anyway, okay, so the last one, greatest common divisor of 1 and n. Um, the divisors of 1 are basically just only 1 and -1. And the biggest of that is just 1. And we also know that 1 divides n. Therefore, GCD of 1 and n equals to 1. Yay, smiley face. Okay, good job. Now that we're familiar with these concepts, we can move on to some actual prime factorization stuff. Like, remember prime factorization from last week? Not last week, last lesson. Yes. Okay. So, um, there's a faster way to find greatest common divisor without guessing and checking or listing them out. Yeah, so you can see here, here's the prime factorization of like A and B, and the greatest common divisor of A and B are just these. Okay, this might be a bit confusing at first, but we can go through the example with like, for example, 60 and 144. So does anyone want to tell me the prime factorization of 60? Actually, I'll give you guys like 2 minutes to find the prime factorization of both these numbers. Okay, Olivia has the prime factorization of 60. Oh, so does Chris. Yay, cookies. Wait, what? I can't cookies anymore. Wait, hold up. Yes, you will get cookies, virtual cookies. So yeah, the prime factorization of 60 is just 2 squared times 3 times 5. Yeah. And then does anyone have the prime factorization of 144? Oh yeah, sure, Kingsley, you can type it. Wait, I'm pretty sure Olivia already got the prime factorization of 144 though. Okay, so that equals to 2 to the 4 times 3 squared. And basically what like this scary looking GCD thingy is saying is let's P1 is just a prime. So that can be 2, right? Whoa. Wait, sorry, my handwriting's also like very bad right now because I'm writing with a mouse. Okay, GCD of 60 and 144 would equal to 2 to the power of the minimum of 2 and 4. What would that be? Yeah, 2. Good job. Um, well, I'll just write it down here as well. Times the second prime. So the second prime
What is
is
the thing after the 2? It's 2 to the minimum 2 comma something.
It's
2
like you want to
4.
find the 2 to the power of minimum of 2 to the power of 2 and 2 to the power of 4.
Whoa, yeah. Okay, I'll explain why later, but let's see how it works first. And then for 3, you can do the same for 3. So 3 is basically 3 to the power of 1. So the maximum of no, the minimum of 1 and 2 is just 1. So 3 to the power of 1. And here we can say, for example, for 144, it's basically 5 to the power of 0, right? Because that's just 1. So the minimum of that is 0. So it's just times 5 to the power of 0. So you end up with 2 squared times 3 times 1, which ends up to be 12. Whoa, we got that in the previous bit as
Wait,
well.
times 5 to the power of what again?
Oh, 0. My bad. Yeah. And if you think about it, like how it works, it makes sense because the greatest common divisor has to divide both A and B. And if any of the powers are greater, like if the prime factorization of the greatest common divisor, any of the powers is higher than like any that A and B contains, then they wouldn't be able to divide that. Do you guys kind of get it? Yeah, okay. Um, yeah, for example, um, if you have 2 squared and you want to divide like 2 squared, then that's obviously doesn't divide 10 because 10 only has 1 2 in their prime factorization. Whereas 2 squared has 2 2's. And like because it's like 4 does not divide 10. Whoa. Oh yeah, thanks for the latex equation. It looks very cool. Yeah, so using this, do you guys want to find the greatest common divisor of 2025 and 120? I'll give you guys 2 minutes, and anyone who wants to share can just scribble on this board later. Okay, does anyone want to share? Yay, cookies. Good job, Olivia. Yeah. So you first prime factorized 2025, which is very good. So it equals to 3 to the power of 4 times 5 squared. And then 120 equals to 2 to the power of 3 times 3 times 5. And then we just look for the common factors, and you end up with, wait, it equals to 3 times 5, which equals to 15. Yay. Okay, I think you guys all understand greatest common divisor stuff pretty well now. Does everyone get it? Oh,
Yeah, I put the text equation in case
Yeah,
anybody needs.
thank you so much. Oh, sorry. Okay, now for lowest common multiple, it's very similar with greatest common divisor, and it's just the smallest positive integer such that both the integers are divisors of it. So here are a few warm-ups. I'll give you guys 5 minutes to attempt all of them because the generalized way is like, yeah.
Here you go.
Oh yeah, good job, Kingsley. Do you want to share how you got that?
The if we start with 7 and we go 7, 14, go up the multiples, and then we have 21, and then 28, and then we get to 35, and then we realize 35 is divisible by 5, and it's the first one that is divisible by 5. So then the LCM is 35. And then if we take 18 and go up there, 18 and then 36, and then we suddenly realize 36 is the first one to be divisible by 12.
Yeah, good job. Okay, so
Yes.
that's a really quick way with small numbers. Oh yeah, cookies. Wait, okay, cookies. Yeah, that's a really good way to do it with small numbers, but I'll give you guys a few minutes to try find a generalized way that we can use for big numbers, just like what we had in the GCD thingy. That looks something scary like this, but like once you dig into it, it's easier, right? Whoa, okay, so there's two very cool ways here. Yeah, do you want to explain your one first, Kingsley? Wait, did you put that there?
Sure.
Yep, do you want to explain how you got that?
Okay. So if GCD uses the lowest power of the common primes, and LCM uses the highest, right?
Mm-hmm.
So then if you take A and A and B and you multiply it together, and you get two sets of the common primes. My pen. Then you get two sets of the primes. So you divide it by the GCD to get rid of the overlap.
Yeah, that's a very good explanation. And yeah, you can basically do that to any number. But that requires you to find the GCD of the two numbers first, which is kind of a hassle. So, yeah. Olivia said you first find the prime factorization and then you take all of the stuff needed. So instead of minimum, it's maximum. Yeah. Okay. That's very good. Do you want to explain it, Olivia?
So like basically if we look at let's look at the 12 and 18, right? So 12 is equal to 2 squared times 3, and 18 is equal to 2 times 3 squared. And then if you look at it, like you would need to like include all of the different stuff. Yeah.
Wow, yeah, okay, good job. So that's actually the thingy we're gonna use, like a generalized way. Because with bigger numbers, I think it's the fastest way you can find like the LCM of a number. Yeah. So over here, wait, it's you can see it. You take the maximum of them. And the reason why you take the maximum is like since A is a divisor of the lowest common multiple and B is also a divisor of the lowest common multiple, then the lowest common multiple of those two numbers have to have at least as much like powers in it so that like A and B can both divide the lowest common multiple of it, right? So yeah, we'll just do another example together so that we get used to the notation. So 12, like Olivia mentioned, was 2 squared times 3. And 18 equals to 2 times 3 squared. And so LCM of 12 and 18 equals 2 to the maximum of like 2 and 1 times 3 to the power of the maximum of 1 and 2, which you end up with 2 squared times 3 squared, which equals to 36. Yay. Okay, I'll give you guys like 2 minutes maybe to try these two questions, like the lowest common multiple of 45 and 30 and A and B when A and B are co-prime. Oh, Cookie, yes, of course. How could I forget? Yay, everyone got the first one right. That's 3 times as many cookies. Now the cookies will continue to grow exponentially. Yeah. I don't think we need to go over the lowest common multiple of 45 and 30, right? Everyone solved it correctly. And yeah, Kingsley is like a different way, but I think that way is also very efficient.
Hey, why'd you delete my text equation?
Oh no, sorry. I like moved it to the bottom because it's like blocking the question. Sorry.
Oh, okay. I'll edit it here.
Yeah. Okay. Yay, cookies. Okay, so I think everyone came to the conclusion that the lowest common multiple of A and B when A and B are co-prime is just A times B, right? And one way to think about it is the way that Kingsley said with his like way of finding the lowest common multiple, because when the greatest common divisor of like A and B are just one, then it's like essentially A times B divided by one, which is just AB, right? But you can think about it another way in terms of the thingy that we just covered. Basically, when two numbers are co-prime, it means that they share no common factors, right? So their prime factorization is completely different. Like, yeah. So then P1, the max of like the two numbers, would be the one that contains that prime factor. So at the end, the number A would be able to contribute A times as many of like the factors to the lowest common multiple, and B would be able to contribute B to that. So in the end, the lowest common multiple is just A times B, because yeah, they share no common factors. Does that all make sense? Thumbs up, guys. Yay, okay. Whoa, so cool. Okay, I think everyone understands lowest common multiple now. So, let's do some useful stuff before we get into the Euclidean algorithm.
Click Z on your keyboard and you get this.
Oh, wow. Okay, so the special properties is like if n divides A and n divides B, then n divides AX time plus BY, where AX, BY, and N are all positive integers, and X and Y are just some positive integer. So yeah, basically we want to prove if n divides A and n divides B, then n divides this thingy for any X and Y that are positive integers. And also the second one is very similar, but it's minus, yeah. And can you guys try prove these? Kingsley, could you please stop drawing on my screen? Thank you. Yay. Okay, I'll give you guys like maybe 3 minutes or more if you need it to prove these. And then from this, we can gain some very big brain insights. So ax is divisible by n and by is also divisible by n. Yes, that is true. Yeah, good job. So Olivia basically has it, and we can write this up more rigorously by saying let A equal to, guys, pick a letter of the alphabet that's not N, A, B, or X or Y. Not A. Okay, C. Oh, Chris says C. Okay, C for cookie. Okay, I'll use K for the next one. Let A equals C times N and B equal to like K times N, sure. Yeah. And then we know that C and K are integers, right? By the definition of like N divides A and N divides B. So we're saying A equals to some number times N. That makes sense, right? So we can rewrite the expression of AX plus BY as C and X plus, wait, is that right? Yeah, K and Y. And then we can factor out the N, which equals to CX plus KY. And we know that that is divisible by N because there's an N in here. And we also know that C, X, K, and Y are all integers. Whoa. So yeah, therefore N divides AX plus BY. Whoa, okay. Oh yes, Olivia wants a cookie. I will give Olivia a cookie. Oh my thing just glitched. Yes. Okay, and we can use a similar argument for question 2. Yeah, does anyone want to just write the question 2 thingy on my screen? Like using the same method? Oh yes, I should probably stop giving everyone virtual cookies because it gives you guys diabetes, but it's okay. Yeah, okay, I'll just write it then. Um, yay. Whoa, and that will be very useful for finding the greatest common divisor even quickly. And if we, for example, have the greatest common divisor with stuff that's not integers. Well, no, they have to be integers, but an unknown integer. Um, Giving out vegetables doesn't give out the same vibe, Olivia. This is virtual cookies. Okay, anyways, so let me introduce you guys to something called the Euclidean algorithm. Okay, so it looks very scary at first, and when I first learned it, it also looked scary. But like once you know how to use it, it becomes very useful. Okay, yeah. So you guys can just read that. It looks very confusing, but I will do this with an example. Okay, for example, if we're asked to find the greatest common divisor of 60 and 24. Whoa, you learned that at school for polynomial division? I think Sophie taught polynomial division in her previous Mine and Z lecture. Yeah, so basically how this algorithm works is that you first write, like, for example, 60 equals to 2 times 24 plus 12, right? And then, oops. And then it's telling you that means that the GCD, like that GCD also equals to the greatest common divisor of 24 and 12. And I will prove this later. And then you can then write 24 as 2 times 12. And then, whoa, you got to this bit. Therefore, the greatest common divisor of 24 and 12 is just 12. And this makes sense because if you let the greatest common divisor of 60 and 24 equal, for example, G, right? If we know that G divides 60 and G divides 24, then from our previous thingy, we find out that G divides 60 minus 2 times 24, right? Therefore, G divides 12. So it's essentially you're repeatedly subtracting the smaller number from the biggest number until you get a number that's, oh my, until you get a number that's like just smaller than your original smaller number, and then you repeatedly do this until you get a number small enough to do like actual calculations on for the greatest common divisor. Does that kind of make sense as to like why it works? Thumbs up, thumbs down. Yay. Okay. You guys can tell me to slow down if you guys want, because yeah, the Euclidean algorithm is like a concept that's kind of hard to grasp. But yeah, if you just remember what we proved previously, this very special thing, then you can just add and subtract stuff so that yeah. And know that this is the greatest common divisor still because we let it be that. And then since we're not doing anything to the bigger number and you're subtracting like a smaller number to it and it ends up as a smaller number, then yeah, the greatest common divisor, there won't be a number greater than the greatest common divisor such that it divides both of them. But on the contrary, if you do something to like the bigger number, the greatest common divisor might get a bit bigger. So try not to do that if you can avoid it. So I have some exercises here for you guys to try the Euclidean algorithm on. Wait, let me just upload them. Whoa, okay. I'll give you guys like 5 minutes to try all of them. Yeah, the Euclidean algorithm is useful for doing exercises with like variables, for example, because then you can't really time factorize them. So yeah. Okay, do you guys want me to do one more example of like the Euclidean algorithm? Because it's like kind of confusing, like kind of a confusing concept to grasp. Okay, I'll do this one. So the greatest common divisor. Whoa, good job, Olivia. Wait, actually, do you want to present your Euclidean algorithm?
Okay, so my Euclidean algorithm is that for 120 and 72, I couldn't be bothered to do anything, so it's just 120 minus 72. Yeah. And then after that, I
So
get
like
48. Yeah.
yeah.
And then now I write 72, 48. Yeah. And then I keep going.
Whoa. Big brain. Wait, hold up. I will give you a cookie soon, I promise.
Okay. Yeah, 72, 48. And then you repeat. Yeah, you get 48, 24 now.
Whoa. Big brain.
And then you want it to be like non-zero. So like that's the last one. So you just take 24. Mm.
Yay. Yay, good job. I will give you cookies. Okay, because of time, maybe try to maybe skip the 2025 one. But um yeah, maybe try the ones after it. Oh my gosh, hi Sophie. Okay, wait, Olivia got the fourth question right. Yay. Wait, does anyone else want to present any of the questions? Okay, I'll just present question 4 then. So the greatest common divisor of a and a plus 1. Oh, okay. Sophie can present that one. Yay. You know that a plus 1 equals to a plus 1. Whoa. Therefore, it equals, oh, wait. Which equals to GCD of a and 1, which equals to 1. Yeah, Sophie, we're covering the Euclidean algorithm right now. What the? Interesting. Okay. Wow, big brain. Okay, do you want to present then? Oh no, why? Okay, anyway, from question 4 though, we can tell that any two consecutive positive integers, they're co-prime, right? And whoa, and that makes sense because, um, for example, if you take any factor of 3, if you plus 1 to it, it obviously won't be a factor of 3 anymore. Yeah. Wait, a multiple of 3, my bad. I cannot English. Okay, so Sophie said GCD of a minus 1 and a squared. So she first said that a squared equals to a minus 1 and a plus 1 plus 1. Sophie, you cannot say much. You were also giving out cookies. I was actually copying you. Okay, so this equals to GCD of what was it? A minus 1 and 1, which equals to 1. Big brain. Okay. Yeah, if you guys want to attempt more of these problems and write them up, I encourage you guys to do so. And yeah, send them to me. My email's just on the handout that got sent out earlier today. Yeah, and to finish off, we can do an IMO problem. Um, I'll send I don't know if I can send the handout in the chat right now, but it's basically everything that we went through today. Yeah, guys, who's gonna solve an IMO problem today? Irreducible means just like it can't be simplified further, by the way. Oh yeah, Sophie. I think you solved this problem before. Yes. Yeah, for example, like 8/6 can be simplified over to 4/3. And then that's irreducible. You solved it before me? Oh no. No, but I also solved this by myself. Yeah, okay, so if it's irreducible, if you think about it, then it means the numerator and the denominator are co-prime. Whoa. Okay, I really want someone to solve an IMO problem right now. Does anyone want to try? Okay, I will present it in 2 minutes. If you guys don't want the problem to be spoiled to you, then you guys can just leave now. Thanks for listening. But if you still want to hear the solution, then you can stay. Okay, well, I guess I'll present it now. This is probably the easiest IMO problem, but it's still cool that, oh wow. It's still cool that you guys will solve an IMO problem. Yes, Kingsley, if you solve it, you will get an actual cookie.
You mean solve any one of those?
The IMO problem. If you solve it, you will get a cookie. Okay, wait. I said I'd present it like right now because I am going a bit over time. Sorry, guys. Yeah, that's what you're trying to prove. Yes, good job, Olivia. Cookies. Oh wait, no. Why is my cookies not working? Okay, I guess Sophie can give you cookies. Yeah, so to prove that they're irreducible, we just want to prove. Oh yeah, WTP means want to prove. I'm just lazy to write it out. That 21n plus 4 and 14. That's like required to prove. I don't like writing that. Okay, and we can do that by saying GCD of 21n plus 4, 14n plus 3. Do a bit of working on the side. 21n plus 4 equals to 14n plus 3 plus 7n plus 1. And then that, so that equals to GC, oh my, GCD of 14n plus 3. Wait, Kingsley, can you move your text a bit, please? Yes, okay, thank you. And then you can do the same with 14n plus 3. That just equals to 2 times 7n plus 1 and plus 1, which you get as GCD of 7n plus 1 and 1, which equals to 1. So you prove that they're co-prime. And then you're done. Whoa. We just solved an IMO problem, guys. Good job. Yeah. So that's all for today. Thank you guys for coming. I encourage you to like write up like a solution for any one of these problems, honestly, because writing it up is very important. And yeah, thanks for coming.